selection is a control structure that breaks the rule that the next instruction always follows the current program instruction.
Another control structure, called iteration, allows the repetition of a group of instructions.
With iteration, software developers construct programs designed to run forever.
Also, iteration enables running a program whose behavior adjusts to the input size.
It should be clear that if a program could not go back and repeat some instructions, even with selection, a finite program would have just a finite set of execution paths.
However, arbitrarily branching the control makes programs difficult to understand by people.
Many tools and mechanisms in programming, for example, commenting on the code, are in place to assist people in understanding and validating their programs.
Structured programming is an approach to software development that proposed some of the first principles for constructing reliable software.
In particular, control structures are designed so that the only point of entry is clear and so is the only point of exit.
For iteration, programming languages offer a more strict iteration operation where the instances of repetition are enumerated.
This enumerated iteration is usually named a for loop.
The body of the control structure is executed for each instance in the sequence.
There is a more general form of iteration where a condition is tested at the beginning of the iteration. As long as this Boolean expression evaluates to true, the body executes repeatedly.
A while loop can implement a for loop. However, programmers should compose a program using those alternatives that make the code more generic and more explicit to be understood by other programmers.
But, low-level programming tools, such as assembly, do not offer the high-level control structures of a programming language.
For example, with MIPS, we implement the iteration control structure with branching operations.
With flowcharts, an iteration is a selection with the possibility of sending control back to an earlier position.
The selection skips the body when the condition is false.
And also, at the end of the body, the control returns to a point before evaluating the question.
Even in C, it is possible to replace a for loop or a while loop with if, then, else and unconditional branching.
Note that the translation in C uses goto, which is called unconditional branching, as control will always jump to the label.
The use of goto in most high-level programming languages has now been minimized in favor of control structures from structured programming.
Nevertheless, translating an iteration into a low-level programming language involves replacing such a control structure with a selection and the minimal use of unconditional branching.
However, perhaps it is more evident that something must affect the variables involved in the condition of the loop, or if the intention is that the program terminates, the code would be incorrect.
Such programming error is known as an infinite loop. Typically, an infinite loop is an undesirable behavior that requires the services of an operating system to terminate the program, or, in more severe cases, the computer must physically be shut down.
Using assembler shows how mechanical computers are. When the code is machine language, it is hard to say, or see, that the code is computing loop.
Consider the following C iteration that adds the integer values in an array of bytes.
The iteration is controlled by a variable I. We name it the index whose initial value is 0.
Of course, this particular piece of C code is equivalent to a piece of code that replicates the body of the while loop 10 times.
While such tenfold replication is equivalent semantics, the code would not be as generic.
Here we focus on the main elements that construct the while loop in MIPS.
Like with a selection, we test a negation of the loop's condition.
Again, when the condition is false, we skip the body in the while loop.
In assembler, if the negation of the condition is true, we skip all the body to the end of the translation of the control structure.
In this case, register T0 is being used for the index I, and register T7 for holding 10, the size of the array.
Thus, the conditional branching test if the index is greater or equal to 10, with target the label named in loop.
The condition appears negated in that the test is for the register holding the value of the index to be bigger or equal to the register holding the value of the bound.
A crucial element of the translation to assembler is the branching back, in this case to a label called loop.
Just before this unconditional branch, we place the instruction that affects the test to exit the iteration.
In this case, it is a direct translation of incrementing the register T0.
Note that register A0 holds the starting address of the array.
Thus, The first instruction is the result of a translation that uses register T1 to compute the address of the ith element of the array.
In the second instruction, a dual used for register T1 appears, since now it loads the value of the ith byte in the array.
Since register S0 is being used for the variable sum that accumulates the addition, the value in T1 is added to such running total.
If the array is not an array of bytes, but an array of integers, there are at least two ways to handle the translation.
The first keeps in register A0 the address for the next integer in the array.
This solution implies incrementing A0 by the size of the word in bytes.
The second approach explicitly computes in T1 the displacement from the base address before retrieving the ith item in the array.
In a loop, code in the body is expensive because it will be repeated as many times as the number of iterations.
Thus, if there is code in the body that does not change, then an optimization consists of removing the constant code from the body.
In this way, the program runs faster.
This optimization is one of the many improvements usually called factoring or refactoring of code.
Efficient code runs faster, keeps the CPU less busy, and saves energy.